started pipelining last time. Today we'll go more in depth on handling the key issues in pipelining, which are really data and control dependencies. This will probably be a fast-paced lecture because I'll go over implementation as well as high-level ideas, and I'll be switching between them. So if I'm going too fast, throttle me. Okay, let's see. This doesn't work because connect the receiving end. You expect it to work. It's like any other communication protocol. Okay. Just a reminders. Homework 3. It's out. Some of you have started. How did lab assignment 2 go? Took a while? Yes. Did you guys start in the last day, or did you guys start a week before? Okay. For this lab, you really want to start 2 weeks before, which means now. Yes. This lab, if the last lab took long, this lab is going to take longer because you're going to design the pipeline implementation. It'll be a lot of fun. You'll learn a lot, but there's no question that this lab will take a lot of time. So this is very important. Start early. Actually, start today. I know some of you started last week when we put up the lab, but I'm not kidding with this lab. Okay? And this is, again, another individual assignment. You can certainly discuss the design options with your other students. That's what I would like to allow here. But you should come up with the pipeline design yourself and implement it yourself fully. Okay? Discussing the design options at a high level is fine, but pipeline design should be different. I don't want to see the same pipeline design from 2 people. And it's usually obvious, right? When you look at the code and when you look at the designs. 2 individual designers usually come up with different designs in general. Okay, and we have extra credits. I won't go into this right now more, but you'll see it in your handout. If you do an early checkoff, you get 5% extra. And we'll reward the fastest 3 designs. Yes? It's specified exactly in the lab handout. I think it's 1 week before. Okay. Friday, the week before. Friday this week, I assume, right? Yes. The fastest 3 designs will be rewarded as well. And this will be more than 5%, I think. So if you actually optimize your design, you can get 10% additional credit. I'll give you the exact breakdown later. I doubt that people are at this stage yet, optimizing their designs. Okay? So we're still covering pipelining. I'm not going to assign any reading for the next lecture because you have a lot in your hands with the labs, I think. But we will augment the lectures with supplementary readings. And go over the pipeline lecture notes very carefully that we have. Actually, the handouts that I gave you, this, along with the, where is this other? Okay, here it is. Along with this pipeline LC3B microarchitecture handout, can help you a lot in designing your lab assignments because this clearly explains what each stage does. Except it's an LC3B, you're supposed to do it for a mix, right? And your book clearly explains some of the things, some of the stages and MIPS. So using these 2 handouts, I think you'll get a very good idea of how you can design a pipeline machine. Of course, you'll do more than what's in this handout. You'll do data forwarding, but we will cover some of those today. And it's also in your book, in the chapter that you've been reading so far. So these 2 handouts are very important. Know them very well. And we'll augment some of the, we'll augment them and the lecture notes with supplementary readings. Okay, there's a calcium seminar. I don't know how many of you attended the last calcium seminar. Anybody? Calcium means Computer Architecture Lab at Carnegie Mellon. So if you're interested in more deeper or research topics in architecture, we have one this Wednesday at 4 p.m. at the D-level conference room. And it's on a different topic, maybe something we don't think of. because you take for granted that computers, at least the hardware, works correctly. It's about embracing errors in architecture. Basically, how do we design the hardware such that it's not correct all the time? And then how do we design the software to tolerate that incorrect execution? You can imagine some software is inherently tolerant of not correct execution, assuming incorrect values appear at the right places. Right? For example, if you're displaying something on your screen, you may not care if your pixels are exactly what they're specified to be. Right? So that application, or if you're playing video, and you've noticed this probably, if you're streaming video, you may not care exactly some part of the screen is exactly displayed as specified or not, right? Because you're dealing with the quality of service that the user receives. And if you make the hardware only as correct as it provides enough quality of service that the user is happy, maybe it's fine, right? You may not need to. Then what you can do perhaps is design your hardware, make your hardware design choices, perhaps such that you can save power, for example. Maybe, for example, maybe if one of the instructions is taking too long, you ignore that instruction, assuming its output does not affect the quality that you provide to the user. So that can potentially make your design higher performance as well as simple and maybe power efficient. So these are some of the interesting research issues that are happening in computer architecture today. Well, one aspect of it. And this talk will be related to designing incorrect hardware and tolerating it somehow at the application level. In this course, we will not cover this. But it's good to stretch your imagination, what you can build, depending on what your goals are. So if your design point is keep the user happy, and if you can keep the user happy by designing incorrect hardware, maybe you're fine, right? Okay. So last lecture, we covered basics of pipelining. We spent a lot of time on overheads of pipelining. What's an ideal pipeline? What's a non-ideal pipeline? What makes the instruction pipeline and non-ideal pipeline? How do we do the pipelining? Why do we need pipeline registers, for example? How do we do the pipeline control, different design options? Do we get all of the control signals right away at decode and propagate them as we need them? Or do we generate the control signals that are needed in each stage at the stage or at the previous stage? And you know the difference between that stage versus the previous stage, right? If you start generating your control signals at that stage, you're already too late. You're lengthening your clock cycle. We talked about some issues in pipeline design, like how to balance the stages, balancing work between stages. And this is usually difficult to do. How to keep the pipeline correct, moving, and full in the presence of some issues, like control and data dependencies and long latency operations. Well, and we will cover more of this basically, how to keep the pipeline correct, moving, and full. Meaning how do we not stall the pipeline? So let me ask you a couple of questions to warm up your caches. What is a stall? What is a pipeline stall? Yes? Exactly. Yeah. Basically, you stop the pipeline, you don't insert another instruction into the pipeline because maybe that instruction's source value is not available, right? Because of some reason. And this could happen at the beginning of the pipeline, but at any stage in the pipeline as well, right? For example, if your instruction is in the memory stage and you need to access memory and it takes more than one cycle to access memory, what do? That instruction stalls in that stage. So the previous stages in the pipeline don't move until that instruction gets its data from memory and it can continue. So that's the idea of the stall. How do you implement stalling? We'll cover this in a little bit more detail today, but your handout explains it, and we talked about it last time. Yes?
You can zero out control signals that will cause destructive operations to occur in future cycles, and you can also prevent the previous ones from updating, previous cycles from updating.
That's right.
So stop the PC.
Exactly. So what you need to do is, let's see how this works. basically, let's take the scenario that I described just now. You have a memory operation in this stage, and let's say it takes, I don't know, 5 cycles, which means that the first cycle it comes into this stage, the load, it should not move, right? Until the memory says, the cache says, I'm ready, and you got the data. This load instruction that's here in this stage should not move to the next stage. So how do you ensure that? Well, basically, while the load instruction is waiting here, the next stage should not receive the load instruction. The next stage should really receive something saying, oh, I'm not really getting an instruction. Right? And that means an OR, right? So that's what Eric meant by zeroing out the control signal. So essentially, this is called the pipeline bubble, if you will. You insert a pipeline, you insert a bubble into the next stage. Or you insert a NOA into the next stage. Into the stage that's after, or into all of the stages that are after, into this next stage that's after the one that's supposed to stall. Make sense? So how can you do that? Well, you could do that in many different ways, actually. You could do that, for example, by ensuring that all of your control signals specify an OR. That's one way. Another way is using these valid bits that I described before. Basically, you can have a valid bit with each pipeline latch, and if the valid bit is 0, all of the control signals that update state, or that do something, that update state essentially, are gated with this valid bit. Make sense? So if the valid bit is 0, these control signals are always gated with that valid bit such that the control signals do not take effect. It's essentially the same thing as changing your control signals such that they don't do anything. Make sense? So that's how you ensure that this instruction does not move to the next stage, and the next stage is essentially a bubble. Well, there's another thing that you should do. Basically, this instruction should stay here, and every other instruction in the previous pipeline stages also should stay. Basically, the pipeline should not move. You ensure that no new instructions inserted, but you also need to ensure that the instructions that are already in these stages do not overwrite each other. So how do you do that? And that's relatively simple, right? Basically, you gate the latching of the pipeline registers when you're stalling. So if there's a stall signal, if you're waiting for memory, that signal is propagated to the previous stages, saying that if I'm stalling, don't update the pipeline register. Make sense? How do you do that? I guess you could do it with a MUX, or you could change the enable signal of the pipeline register such that they're not write enabled if a later stage is stalling. Simple. Okay. So that's how you need to, on a stall, basically two things. Insert a bubble or NOA into the next stage. Ensure all previous stages and the current stage stay the same, right? If you don't overwrite. So this also includes, if there's an instruction that's being fetched here, you'd better not overwrite the program counter, right? Because if you do overwrite the program counter with the next instruction, then you have a problem. Okay. So we'll cover this, how to handle the program counter in more detail. So if you look at this particular design, yes?
Are all the valids bits tied together?
Are all the valid bits tied together? No, right? They should not be. So if you look at...
But if you don't want one stage is bypassing forward, you don't want all the others to move forward.
So the stall signal goes to each of the valid bits, but the logic that determines whether or not this particular stage is valid is different, because there are really different stall conditions that affect different stages. So, for example, in this case, if you look at the fetch stage, this is the fetch stage of the LC3D. Basically, you have the program counter that's accessing the iCache, and at the end of the cycle, in the fetch decode pipeline latches, you'll hopefully have the instruction bytes, and you also have an update of the program counter here. So this logic determines whether the thing that you insert into the next stage is valid or not. And this logic, there should be inputs to it. For example, if you have a stall here, meaning you're trying to fetch the instructions, and let's say this takes more than one cycle. In your pipeline, this will not happen. But in a realistic pipeline, this can happen, right? It takes more than one cycle. You should insert a bubble into the next stage, right? If this takes more than one cycle. But, which means that, but this happens only in this stage, right? You should not insert a bubble into stage X downstream, because there's something else happening in that stage. That's why these valid bits are not tied together. The logic that determines this valid bit is different from the logic that determines the later valid bit.
Why not just like solve all of them? Because they're all going to be tied together, right? Like they're all going to be like 5 stages.
So, okay. I think if I understand what you're saying, some stages can be moving while some stages can be stalling. So this stage can be, if you look at this, let me give you an example. Here. For example, you may be fetching instruction at program counter N here, and you're waiting for the memory to respond. But you may have an add here. Actually, you may have many adds here, let's say. That you already filled the pipeline. But now somehow you got a cache miss here. You're waiting for the memory to respond. What you need to do is really to keep fetching this instruction in this stage, but you can move all of the other adds. Right? Let's say this is add 1, add 2, add 3, add 4. This is the first cycle. In the next cycle, what you would really like to do is still fetch from PCN, but have a no-op here. And you would like add 4 to move to the next stage, add 3 to move to the next stage, and add 2 to move to the next stage, and add 1 to finish. Make sense? That's why the logic is different. Yes?
So memory is sometimes asynchronous, right? So how can you determine inserting no-ops like dynamically coming in?
Well, you need the logic that we described previously, right? Memory needs to tell you when it's ready.
Right.
So there needs to be a bit saying that I'm ready now, so you can start moving the pipeline. Yes?
So you need to stop all instructions that are behind the current instruction, right? But
Exactly.
You're only determining the logic in the current instructions. How do you make sure you're stalling all the previous instructions?
Okay, so that's the purpose of sending the stall signal to previous stages. So you need to send the stall signal to previous stages also. Well, in this stage, it doesn't matter because there is no previous stage. But for example, here, there is a dependency check logic that checks whether the instruction you're currently decoding is dependent on any later instructions. And if it is dependent on any later instructions, or any instruction in a later stage, this generates a stall signal which is sent to the previous stages. And this stall signal is used to gate the latching into the pipeline latch. Make sense? That same stall signal is also used to insert a bubble into the next stage. So you will need to propagate the stall signal to previous stages. So these two things are achieved in different ways, right? You insert a bubble into the next stage. I guess you can ensure next stage is invalid. And ensure all previous stages and the current stage stay the same. So all previous stages, if you look at this, how should you do this? Basically propagate a stall signal to all previous stages. Okay? And if you look at the pipelined LC3D design, there is a stall signal that's generated here. If you look at the decode stage, this is explained in detail in your handout. One of the things that happens in the decode stage is we check whether the instruction that's currently being decoded is dependent on any other instruction that comes that is later in the pipeline. We should not move this instruction if the data value for this instruction is not available yet. And if it's not available yet, that availability is determined by this dependency check logic, which generates a stall signal that's propagated to the previous stages. Okay? And you can actually see that there are other stall signals. Let me give you one more example here. Not all stages generate stall signals, right? If a stage does not necessarily stall, you may not generate a stall signal on the stage. For example, here, there is a memory stall signal that's generated. If the data cache misses, for example, if it doesn't respond in a single cycle, a stall signal is generated that's sent to previous stages. Okay? Okay. Okay, let's look at one other question. We're still reviewing, but we're also covering new material. I'll get back to the stall signals in MIPS in a little bit. So we discussed there are two ways of detecting dependencies. Right? One is scoreboarding, and the other is hardwired combinational logic. Do you guys remember? Yes? Greg remembers. So what are the advantages of detecting dependencies using scoreboarding? Simple hardware, yes. It's simple hardware because you have a single bit associated with each register saying, is there an instruction in the pipeline that is going to write to this register? And any other instruction that's coming in checks that bit, assuming it's sourcing that register. And if it's sourcing that register, and there's some instruction, and the bit is not valid, then the instruction stalls. They basically generate a stall signal. This is very simple, right? Combinational logic is a little bit more complex. But there is an advantage to it in the sense that what if there are multiple instructions writing to the same register in the pipeline? That scoreboard becomes more complex too, right? You have to handle that the valve is updated at the right time. Okay? So you can think a little bit more about that. We covered this last time. Okay. So this was one of the later things we discussed. One way of ensuring that your pipeline moves correctly is to have the compiler reorder code such that the hardware doesn't need to detect data dependencies. So, I guess we'll need to switch this way. Okay. So if you look at this pipeline, if the compiler somehow ensures that the pipeline is always moving, for example, when this instruction, if the compiler ensures that when this instruction gets to this decode stage, the data value that it needs is always available, then you don't need this dependency check logic. Because the compiler somehow ensured that the instruction that's producing the register that this instruction in the decode stage needs has already produced that value because it's separated those instructions enough in terms of the number of instructions that that instruction is already written into the register file. Make sense? So this is one way of handling the dependence in a pipeline. So what is the advantage of this? Yes?
It makes it simpler in your hardware.
Yes. It makes the hardware simpler, right? Hardware doesn't need to implement this dependency check logic now. What about this advantage? Yes?
You're putting a lot of trust in your compiler. And the other thing is you're lowering the flexibility, because if you do it in hardware, you can make assumptions about, even if you don't have that compiler, then your
right.
hardware will handle it. But if not, you have to.
That's right. Those are good points, actually. Yes. So let's take a couple of them. The first thing is, you said you're putting a lot of trust in your compiler. So if your compiler actually is buggy, for example, you can get incorrect execution, right? Assuming you didn't have that dependency check logic. If the compiler forgot, if you will, to do this. Let's assume the compiler is correct. But if the compiler is not able to find anything, right? Meaning, maybe there is no way that you can actually put useful work, if you will, to fill the pipeline to ensure that a data dependence between, let's say, you have an add instruction that's writing to register 1, and then you have a multiply instruction that comes right after that, that's reading from register 1. You would like these to be separated from each other, such that when the multiply is trying to read the register values from register 1, add is already written to R1. Which means that, so where does add, let's ignore this one for now. So add stores its result here into the register file, right? So add should be out of the pipeline. So multiply, when multiply is being decoded, add should be out already, out of the pipeline, which means that the compiler needs to find 1, 2, 3 instructions between add and multiply, right? Does that make sense? Did you figure out how I did this? Basically, add writes its result into the destination register here, right? We're not assuming any data forwarding in this case. And hopefully you remember the data forwarding idea. Add finishes writing its result at the end of the store result stage here. So multiply should really be decoded right after add finishes writing its result. Which means that there has to be 1, 2, 3 instructions between the add and the multiply. Right? So how does the compiler find those 3 instructions? Well, what the compiler can do is look at some other parts of the code and find work, other instructions that can get in between add and multiply. But of course, these instructions need to be independent of both, right? You cannot have an instruction here that's, I guess that's writing to R1, for example, ordered here. Or another instruction that's reading from R1. You cannot place that here. So, finding these 3 instructions may be difficult to do. Especially if you have a lot of dependencies in your code. And there's also the question, what if you have a branch instruction here, right? How can you move the code? Because you're doing branching for a reason. Okay. So, what happens in many cases is the compiler actually finds, well, what if the compiler doesn't find useful work to put between add and multiply? I already gave you the answer, I guess yes. It needs to ensure correct pipeline operation, it needs to insert no-ops here. It could insert 3 no-ops if it finds no useful work to put between add and multiply. It could, if it finds only 1 instruction that could be placed between add and multiply, it could insert 2 no-ops and that instruction. So of course this reduces the utilization of your pipeline because a no-op is really not necessary, right? That's not, well, you're not doing anything basically. You're not helping the performance. So if you think about this insertion of no-ops by the compiler is really similar to this insertion of the bubble, right, in the pipeline. You're really inserting a bubble. This is inserting a no-op. Except here the hardware is doing it. Here the compiler is doing it. Make sense? Yes?
Y3 instructions?
Y3, well, it depends on your forwarding path. So when I here, maybe it's better to do. So if you look at here, this is the store result stage, right? Add writes its result into the register file in this whole cycle, in the store result stage. And the value will be available at the end of this, meaning add should be out of the pipeline. So multiply can read that value only after add is out of the pipeline, which means that there has to be 1, 2, 3 other instructions between the add and the multiply. So that depends on your assumption of the forwarding. And I'm assuming right now there's no forwarding at all. Add writes its result gets latched into the register file at the end of the store result stage. And for the multiply to be able to read it, it needs to come to the decode stage in the next cycle.
If they had register file writes and reading occurring in the same cycle.
That's right. So that's one kind of forwarding. If you could do that, then yes, then it's 2 instructions. You're right. But that's one way of implementing, right? The design. And I will cover some of that very soon. Okay. Okay. So this is called essentially software-based interlocking. Remember, we use this term, software-based interlocking. Here, the software ensures that you don't have, you don't need a hardware-based dependency detection logic between instructions. Okay. So this is what we've covered. I guess in the review I covered some of this also. Let's go in a little bit more depth in some of these. Remember, cause of pipeline stalls, resource contention, dependencies, and long latency operations. And we've covered resource contention. Let's look at dependencies. I thought I had the resource contention slide. Okay, let's do this. Resource contention happens when instruction 2 pipeline stage need the same resource. You could eliminate this, and we talked about ways of doing it, or you could detect the resource contention and stall one of the contending stages. Okay. Now let's go to the dependencies. Remember, these are also called dependencies, and there are 2 major types, data and control. And they both disrupt the pipeline flow. And you remember the flow, output, and anti-dependencies, right? Okay. I'll go through this quickly. Okay. So this is the read after write dependence, and this is what we will be concerned mostly about because this is a real dependence. You really need the value here. Whereas if you had, I told you that if you had infinite number of registers, this is really not a dependence, right? It's really just because you ran out of the register names that you had to do something like this. If you had infinite number, you would rename this register, if you will, to register 1 billion, for example. Because the value in this register 1 has no connection to the value in this register 1. Make sense? Similarly, for the output dependence as well. Okay. Basically, if you write to the destination in one stage and in program order in a pipeline machine, you don't need to worry about these 2 dependencies. These 2 dependencies start mattering if you start executing instructions out of order. Meaning if you execute this instruction earlier than this instruction, then you need to ensure that this instruction gets the correct value of R1. Make sense? And we will briefly cover that when we get to it. Flow dependencies are more interesting in a pipeline machine, and that's what we've been talking about, right? How you detect that dependence and stall the pipeline. And remember, we covered 5 fundamental ways of doing it. You detect the flow dependence and stall. That's what this LC3B microarchitecture does here. Basically, you have a dependency check logic that detects the stall dependence and generates a stall signal that detects the flow dependence and generates a stall signal such that fetch stage stalls, decode stage stalls, and bubbles are inserted until this dependence goes away. And when will this dependence goes away? When the rest of the pipeline moves, this dependency check logic at some point evaluates to 0. The stall signal evaluates to 0 because the rest of the pipeline moved and the instructions that needed to generate the value that's needed by this instruction here already generated that value. Make sense? So that's why you need to ensure that the rest of the pipeline moves. If it doesn't move, then you're really deadlocked. Right? And you can get actually deadlock issues in a pipeline if you don't ensure correct movement of the later instructions of the pipeline. Yes?
Does every stage have its own dependency check logic?
That's a good question, actually. In this case, in this LC3B implementation, this is the only place where we check for dependencies. Because there's no forwarding assumed. There's no data forwarding. Which means that if there's any instruction that is in the later stages writing to this register, we better stall this instruction because there is no forwarding path. This instruction, if it moves to the later stage, it will not get the correct value. Okay? But if you add forwarding, then now there could be other things. Okay? And we will see that in a little bit. If you add forwarding, you need to, you can move the instruction to the later stages, but you need to ensure it gets the value from the correct bypass or forwarding path. Okay. Oh, I guess this doesn't work because I need to do left. Okay. So detect and stall is one way. Detect and forward, bypass the data to dependent instructions is another way. And I will cover this in more detail. So we may not really need to stall, as I told you in the previous lecture. Right? So, for example, actually in this, maybe we will cover it quickly in one of these things. So if you look at the LC3B pipeline, let's say you catch that add instruction that's writing to R1. Can you guys see that? Okay. And let's say we're decoding a multiply instruction that's reading from R1. Now this multiply instruction is dependent, and add instruction is producing R1. Right? If we stall on data dependence, when will this add instruction really write to R1? What we need to do is, this is, let's say, cycle 1. I guess I'm not very well coordinated when I'm writing onto the stock camera. In cycle 2, if you're stalling, multiply should stay here. You'll have a no-op here inserted, a bubble, I'll call it. Add will move here. Now, let's do this. Okay. There you go. In cycle 3, multiply should still stay here because add hasn't written back to the register file. Add will write back to the register file in the store result stage. You'll still have a bubble here. Insert another bubble. This bubble will move to the next stage, and this add will move to store result. And remember, add will finish writing its result into the register file at the end of the store result stage. So in cycle 4, multiply should still stay here. You'll have another bubble here. the previous bubble, basically you're moving the pipeline, right? We inserted a bubble here, and this bubble has moved to the next stage in the next cycle. Now the previous bubble has moved to the next stage in the next cycle, and we've inserted another bubble because this multiply still cannot move. And this bubble moves to the latest stage. And now add is out of the pipeline. Add is already written to the register file. Now the register file is actually ready. Right. This multiply can now move because register 1, there's no instruction in the pipeline that's writing to register 1 because all other instructions in the pipeline are really bubbles. They're not instructions. Right. So now the multiply can move to the next stage after reading R1 and can do the computation. So if you look at this, we really wasted 3 cycles, right? No forwarding. We really wasted 3 cycles. Even though add results was really available at the end of this cycle, right? Because add executed here, and it really generated a result at the ALU. Well, actually here, right here. But we waited to execute multiply until that result actually got written into the register file. There was no real need to do this. Right? What we could have done is to take this result and, well, not to that block maybe. Remember I drew this before. I'll go into more detail today. But what we could have done is to forward this value from the ALE output. That way, we wouldn't have wasted 3 cycles. After the add executes at the end of this cycle, in the next cycle, now we can move the pipeline, right? Multiply is waiting for the result of R1. Here, add is generating the result of R1. In the next cycle, add moves to the next stage. And multiply can now move here, right? Because it captured the value of R1 through this additional tag. Okay? So that's the idea of data forwarding. And you need to add forwarding or bypass paths to send the data to dependent instructions. Okay, we've covered this. Another way of handling is software-based interlocking so that there is no need to detect. We've covered do something else. We'll get back to this, right? This is a less conventional approach. Actually, this is an approach that was used in old supercomputers, fine-grained multi-threading. If you had a lot of threads in your system, why not fetch from a different thread into the pipeline every cycle? It's like that you never have instructions that are dependent on each other in the pipeline. That way you don't care. That way you don't really need to detect dependencies either in software or hardware, right? Because you already have enough threads. And a more advanced thing is predict the needed values and execute speculatively. Let me spend a little bit more time on this. So when well, maybe this add is not a good example, but if you have a dependent instruction and its value is not ready, one option is to guess, right? Guess the value. If you're right, that's great, right? Then you don't need to do anything later on. If you're wrong, now you have a problem. So first of all, if you guess the value and let the pipeline move, you need to check whether you did the right thing. So this idea is called the idea of value prediction. And we will see it as a special case in terms of handling branches. So this is the idea of value prediction. The idea is to predict the value in the register. And even before the value is available, assuming if the value is not available, of course. If the value is available, it doesn't make sense to predict it. And then check if correct when the value becomes available. And if you're correct, I guess correct, no action, right? Because you've done the right thing. Whereas if you predicted incorrectly, then it becomes a little bit hairy. You've already moved the pipeline, right? And executed with the wrong value. Now what do? Well, first of all, you need to ensure that that wrong value never updates the register file. That's the first thing. But you also need to re-execute the instructions. So this is basically, there's an action that's called flushing the pipeline. One way of doing it. You flush what happens in the pipeline and re-execute from the instruction, beginning with the instruction that you predicted, that you value predicted, if you will. So I'll give you the high-level idea of this, and you can think about how to implement it. But you need to, of course, keep extra state to ensure that you can do this. But this is one approach to handle data dependencies. And I'll let you think about it. Okay. Interlocking. You remember the terminology. Okay, I'll skip this because we've already talked about it. This is just let me get you thinking a little bit. We will probably get to control dependence toward the end of this lecture, or maybe in the next lecture. We'll definitely cover how to handle control dependence. But this is really a special case of data dependence, right? So what is control dependence? The instruction you fetch is dependent on what other instructions you executed previously. If you have a control flow instruction, definitely you're control dependent on the execution of that instruction, right? And control dependence is really a special case of data dependence, if you will. Because which instructions update the program counter? Say it again? Jumps and branches definitely update the program counter. All of them. There you go. That's the right answer. So now you know how to answer that question in an exam. All instructions update the program counter, right? At least in a von Neumann model. Some instructions trivially update the program counter, if you will. PC equals PC plus 4, for example, in MIPS. But some instructions do more interesting things. We call them the control flow instructions. But program counter is really a data value that you source in each instruction. You can think of it that way. So it's really a data dependence on the instruction pointer or program counter. So you could use all of the techniques we discussed, if you will, to handle this control dependence. But it's a special case because, if you will, this control dependence is very disruptive to the pipeline, right? Because what should the fetch PCB in the next cycle? It's really at the beginning of the pipeline. You don't know what to fetch if you don't resolve this dependence quickly. Meaning that you're not able to fill your pipeline if you don't handle this dependence very well. That's why this special case is very important in designing a pipeline. Because you fetch an instruction, you have the program counter here. What should your next program counter be? What instruction should you fetch next? Well, if we take the approach of stalling, then we cannot fetch the next sequential instruction, right? Because we don't even know if the instruction will be the next sequential instruction. Okay. So Answer is, do you really want the address of the next instruction you're really going to execute? Well, we already covered this. If the fetched instruction is a non-control flow instruction, so next fetch PC should be the address of that next sequential instruction. Make sense? In MIPS, this is PC plus 4. And it needs to determine if you know the size of the fetched instruction. Here, again, remember the variable length, fixed length ISA? If you know the size of the instruction, this is very easy to determine. If you don't, then you have to somehow find the size of the instruction that you just fetched. If the instruction that's fetched is a control flow instruction, then this becomes more difficult. How do you determine the next fetch PC? Because that control flow instruction, well, depending on which control flow instruction it is, may not resolve until it's executed, right? Actually here, for example, in the LC3D pipeline, a conditional branch doesn't resolve until this happens, until this branch logic evaluates its condition. But you don't have any. What do you do to the pipeline in that case? Basically, you insert bubbles again, right? If you're stalling. Or maybe you do something else. But even before that, how do you even know whether or not the fetch instruction is a control flow instruction? You don't even know that in the fetch stage, right? If you look at the fetch stage, all it does is accesses the iCache of the program counter and brings the instruction bytes. You figure out whether or not an instruction is a control flow instruction in the decode stage. But you really need the address of the next instruction while you're fetching this current instruction. So that's the problem of control flow in a pipeline machine. You don't know what your next PC is during the cycle you're fetching this instruction, but you really need to determine that next PC while you're fetching this instruction. Okay. So there are different ways of handling this, and we will cover that later on. So I think I will leave you with this question for a while, so that in the next 5 minutes where we take our break, you can think about it. And I'll go into more detail in data dependence handling. Is that good? Let's take a 5-minute break. Okay. Do you prefer to take the breaks, or do you not prefer to take the breaks? Take them? Okay. Do you prefer longer breaks or shorter breaks? I guess that's the next question. 5 minutes is good? All right. Okay, let's go into a little bit more detail, and I will probably go through this relatively fast because I gave you the high-level ideas. The implementation, there are interesting implementation issues also, but I will have you sort some of these out on your own, because you'll have to do that anyway for your lab. Okay, so this is a reminder slide, and there were several ways of handling it that I just discussed. Basically, the issue is if you have flow dependencies, these lead to conflicts in the 5-stage pipeline. Remember, I'm going to assume this 5-stage pipeline. Actually, LC3D is designed to follow this 5-stage pipeline also, so it's going to be very generic. But basically, you have this write-back stage, and the result of this write-back stage is not available. The result of an instruction is not available until it writes its result in the write-back stage, right? Which means that if there are any instructions in the pipeline that need that value, here add is writing to RA, and these instructions are reading from RA, then you have a conflict in the pipeline. And actually you have a conflict here too. You correctly pointed out that if the register file does internal forwarding, if you will, if you can write to the register file and read from it in the same cycle, maybe maybe you don't have a conflict here in that case. So here, you have the data value available, all right? Once this instruction writes to the register file here, this instruction can read. But all of these instructions would have gotten wrong values if you move the pipeline. So if you analyze the pipeline as to when there is a potential conflict, between two instructions, you can do something like this for the MIPS-like machine, right? And you will need to do something like this. This is your 5-stage pipeline, and these are the instruction types. You can do a chart like this, denoting when each type of instruction reads the register file, and when different types write into the register file. And let's constrain ourselves to read after write for now. So you need to ensure that when a type of instruction is reading from the register file, the instruction that's producing that value is already written to the register file. So let's take a look at how this could be kind of formalized, if you will. You have a distance between the instructions that are dependent in terms of read after write. Let's call that distance I, comma j. Instructions are I and j. And you also have a distance between the stages, if you will. Right? If the distance between the instructions is less than the distance between the stages they're in, then it's unsafe to keep j moving. Right? This is you should never get into this condition. You have to separate the instructions far enough. Whereas if you keep the distance like this, the distance between the instructions greater than the stages, the distance between the stages where one is writing and where the other is reading, then you're safe. So all you need to satisfy is to ensure that that distance between the instructions is greater than the distance between the stages where one writes and the dependent instruction reads. And you can do a similar analysis for write after read and write after write dependence, but we'll not concern ourselves with that for now. So basically, you can generalize this and say instructions IA and IB, where IA comes before IB, have a read after write dependence, if and only if this condition is true. IB of this type reads a register written by IA. And IA has to be of this type because no one else writes to that register. And also if the distance is less than or equal to 3. Why 3? Because that's the distance between the number of stages where a write happens and a read happens. Okay, so to resolve this data dependence, let's assume the distance between your instructions was only 1. I is writing to Rx and J is reading from Rx, and the distance is only 1. So how do you resolve this data dependence? Basically, when you fetch J, you need to ensure that that distance really becomes greater than 3. Right? So this is a little bit more of a formal analysis of the pipeline, and you can actually think about extending this to generate pipelines, if you will, which we definitely will not get into. But that's what pipeline stall is really doing, right? It's ensuring that the distance between the instructions is really greater than the distance between the write and read stages. And you could do this again, as I said, by stalling the pipeline, by inserting bubbles, or by doing this. The software-based interlocking, injecting knobs at the software level. So a stall is really making the dependent instruction wait until the source register value is available, and we already figure out how to do this, right? Basically, you want to stop all upstream stages, if you consider these stages upstream, and you want to drain all downstream stages. And that's what we discussed. So how do you implement the stalling? We've discussed this also. Basically, you need to disable latching of the new instructions into the pipeline, and ensure the stalled instruction stays in its stage, and ensure none of the previous stages move. And insert invalid instructions or no-ops into the stage following the stalled one. And you can read in your book, and you're going to design something similar to this anyway. But the concepts are the same. Whether it's an LC3B, whether it's an MIPS, this is the microarchitecture design, right? You got to ensure this happens. So how do you determine the stall conditions? Well, this is it, right? Instructions IA and IB. Whatever I told you before, right? You've got to figure out whether there's an instruction writing to the register that the previous instruction needs. In other words, we assume no forwarding still. You must stall IB, instruction B, in ID stage, if it wants to read a register that's written by IA in execute, memory, or write back stages. So you're going to check whether the instruction in execute, memory, and write back is writing to a register, and that instruction's destination is the same as the source register of the instruction in the decode stage, and if the instruction in the decode stage actually needs that register. So if all, this is one specific case where if the instruction in the decode stage needs RS, if you will, and RS is the same as the destination of the register that's being written in the execute stage, and the instruction in the execute stage is actually writing to a register, then you got to stall the instruction that's in the decode stage. Make sense? And you got to be comprehensive. So this is checking whether the memory instruction in the memory stage is writing to the same register that you're trying to source. The instruction in the write back stage is writing to the register you're trying to source. And also, you need to ensure that you check the correct registers, right? Some instructions are using RT versus RS. Right? You can have two source registers. You have to do this for all of your source registers. Okay? So this is really the logic you need to implement. I guess I've given away the logic. But that's okay. Okay. Well, what is use RS? You can figure that out, right? It returns true if the instruction actually requires that RS, if you will, the source register. And it could be RT also. And of course, it's not R0, right? Because R0 is really 0. Okay. And we already discussed this. Okay. So stalling, if you think about stalling, it's kind of bad, right? And I've shown you, this is more of a formal analysis, if you will. Each stall cycle corresponds to one lost ALU cycle. And if you have S stall cycles in your program, you're really losing in terms of cycles per instruction, right? So whenever you do stalling, these data dependencies and also control dependencies affect your performance in this sense. They increase your cycles per instruction, right? Because you need to stall. So we would like to really minimize the number of stalls. Of course, this S really depends on how often you have read after write dependencies, right? You can have a program where there are no dependencies. In that case, your S could be 0. That's a perfect pipeline, remember. It also depends on the distance between the dependent instructions, right? If the compiler did a really great job, then you may not need to stall, right? Of course, great job is not adding no ops, right? This is another way of stalling at the software level, if you will. And also it depends on distance between the dependencies themselves. Okay, so if you look at this code, this is from your book, and this has lots of dependencies. It turns out you need to stall quite a bit in the MIPS pipeline. You see there are 3 stalls between this add and shift left, because shift left needs S1. Set less than, sorry. Yeah. I confuse all of these. This is shift left, right? Okay, shift left logical. And yeah, that shift left logical generates the value of the add, so that needs to stall. So we would like to do something other than stalling, and we already know the concept of forwarding, right? Basically, you don't really, if the value, register file is again a name for the value that you're communicating. If you have the value produced or registered, essentially, what you would really like to do is to communicate value produced by instruction, I guess source, I'll call it, IS, to consumer instruction, IC, I'll call it, or destination ID, let's say. And register file just provides a medium to make that communication happen, right? But that's not the only way of doing it. So as long as that value is available and you can provide the hardware, you can communicate that value in many different ways. Right? You don't need to wait until that value is written into the register file. Similarly, you don't need to wait. If you have a store and a load, for example, you don't need to wait for that store to write its result all the way into memory to send that data to a load that needs that result. If the values are available, maybe you provide a path that's separate from the memory, separate from the register file, such that that value is communicated. And that's the idea of data forwarding. You're providing a path to communicate the values from the consumer, from the producer to the consumer. Okay? You can think of instruction communication this way. In a sense, register file, even register file is an abstraction, right? What you really care about is the communication of that value. Okay, you can read this on your own. Basically, that's what this is saying. What matters is really you need to maintain the correct data flow between operations. So what you can, okay. Oh, so that didn't work too well. That's what happens when you press the wrong button. Okay. So how do you maintain the correct data flow? As I said, don't wait until you write the value into the register file. Figure out when the data value is available earliest, and start executing and provide a way of sending that value to the dependent instruction such that you can start executing the dependent instruction in the next cycle. Right? That's data forwarding. So how do you resolve data dependencies with forwarding? Now you need to have logic to enable this, right? Well, basically, if you look at this particular case, for example, if you have a forwarding path, you don't need to stall here, right? You can retrieve the operand from the data path instead of the register file. But what you need to do is you can have multiple forwarding paths, right? So let's say you have an add instruction here. Let's assume this is ignore this for now. Add instructions being decoded in this stage. And there are other stages, execute memory write back. And add instructions, let's say sourcing one register, register 1. Where does the add instruction get its register 1 from? All of these instructions could be writing to register 1. Or maybe only one of them is writing. Or maybe none of them is writing. So you need to check which stage is producing the value that this instruction in the decode stage needs. So you could actually have forwarding paths from any of these stages, right, to the decode stage. And this instruction, there needs to be logic that checks, that gets the value from the correct stage. Does that make sense? So maybe I'll go a little bit more detail into this. You have fetch, decode, execute, memory, write back. If you have an add instruction in the decode stage that's reading from register 1, now you can have an add instruction that's writing into, well, let's say, register 1, that's writing into register 1 here. Or you could have an add instruction that's writing into register 1 here. Or you could have an add instruction that's writing into register 1 here. Let's assume this is the case. This add should get the value from this stage, right? Not these stages. But there should be paths, if you want to have the full forwarding, there should be paths from these different stages into the decode stage. So essentially, what is forwarding? I'll get into a little bit more detail, but you have a result here at the end of the ALU, if you will, that is available. You have a forwarding path from this stage. Let's do it this way so that we don't complicate the board, if you will. This is the forwarding path. Well, add instruction can get, the add instruction, the decode stage, can get its value from the register file. Or it could get the result of this previous add from this forwarding path. Or it could get the result of this next add from this forwarding path, right? Because it depends on the distance between the instructions. Or it could get the result of this add, right? So you have 4 possible places where this dependent add instruction can get its value. Register file, execute stage, memory stage, write back stage. Yes?
What happens if you have an add, and then before that add, maybe you have some sort of like load word? So the add's writing in the execute. Load word's writing in the write back stage. And they're both writing at the same time.
Writing where?
Into the register file.
So register file writes happen only here, right?
Okay, then they both write forward their information at the same time.
Then the dependent instruction should pick the one, right? There should be logic that picks. You cannot get your data value from both instructions. Well, you could, I guess, as long as they're different sources.
Okay.
Yeah. But the same source cannot come from both of the instructions, right?
So you basically have to know all the instructions in front of you.
Exactly. Yeah, that's what I'm getting at right now. You're thinking ahead. So you need to basically have logic that determines which stage that your value is coming from, right? So there's control logic for this mux, and you can design it. Basically, I'll call this the data source logic, for lack of a better name. You basically determine where the value of R1, one of your sources, needs to come from. Right? So to remember this picture, we'll get back to it. But you can have many data forwarding paths. So this is kind of a simplified version of the MIPS you're going to do. Basically, you can have a forwarding path from the end of the ALU. And this is the mux that I drew over here, right? You can get your data value from the register, or if the instruction that you're dependent on is ahead from you with a distance of 1, if it's the next, right previous instruction, you can get the value from this forwarding path. If the distance between the consumer instruction and the producer instruction is 2, which means that you have somebody writing to the register that you need here, but the next instruction is independent, then you get the value from here. If the distance is 3, and there's another forwarding path from here, right? Or you could kind of think of it as internal forwarding, if you will. If you're in this stage, maybe you write to the register file and you can read the register file in the same cycle. That's what's assumed in the book. Okay? But really, you could do this also. It's really forwarding from this stage. Okay? So these are the different forwarding paths. Now you need to design the control, if you will. This is the forwarding unit. I called it the data source logic. You could call it the forwarding unit. Determines the control of these muxes. And we will see how you can control it. Well, it's simple, right? Basically, you need to figure out if you're writing to the source. Well, let's get to it. There's another way of designing the forwarding paths, which is here we put the muxes before the pipeline register. You could put the muxes after the pipeline register, right? For example, in this case, ALU produces result and latches it, and in the next cycle you forward the value to the beginning of the mux. Okay. It's just a different way of design. And it depends on how you balance your pipeline, really. There's no best way of doing it. Yes?
If I'm with the code stage and you're dependent on something in the memory state, or correct that, if you have a distance of 1, and you are dependent on something that's in the memory stage, would you still need to insert a bubble?
Exactly. Yeah, well, we'll get to it. You're thinking ahead. You're right. You cannot. I mean, this will not cover all possible cases, because there are cases where you will not be able to move the pipeline all the time. But that's good. Okay, this is the other forwarding path here. Again, this is the version 2, if you will, where we put the muxes after the registers. And where you put the muxes, again, depend on how you balance your pipeline. And this is the third forwarding path. And here the assumption is you go through the register file. Okay, this is more like your books pipeline, if you will. Okay, so what is the data forwarding logic? Well, it's a little bit more complicated, but it's not that bad. Basically, if you're so this basically determines where do you forward, assuming this pipeline, basically ALU results is latched. After that, you forward the data. You need to forward the data to the instruction here, if you will, if the destination of the instruction that's in the memory stage is the same as the source register of the instruction in this stage, and of course if the source register is not 0, and the instruction in the memory stage is actually writing the register. Right? That's your control in that case. Well, this is a prioritized logic, if you will, because if you can't forward the data from this state, you should forward the data from this state. If the producer is here, you should get the data from here. Let's say this evaluates it to 0, meaning you cannot forward from here. Then the logic needs to check if it can forward from here. Right? And it's the same thing. If the instruction in the write-back stage is writing to the destination register, the instruction in this stage is sourcing, and the destination source register is not 0, and if the instruction in the write-back stage actually is writing, then the operand is forwarded from the write-back stage. Otherwise, operand is gotten from the register file. And we're assuming internal forwarding here. Okay? So this is simple. And you'll need to do this in your lab. Well, I've already given you that. Okay, so with forwarding, what we've really done is we've changed where we produce the values. Right? For example, R-type or I-type instructions actually produce their values now in the execute stage. They're not. Remember, in the earlier, without forwarding, production happens in the write-back stage, right? For both R-type and I-type instructions. Now we've moved where that production happens, if you will, by forwarding that path, providing that forwarding path. But as you said, memory instructions obviously cannot produce their values in the execute stage, right? Because they haven't accessed memory yet. So a memory instruction has its data value, load instruction, let's say. Load word loads from memory only at the end of the memory stage. Which means that if there's an instruction that's dependent on it immediately afterwards, well, you should stall it at this point, right? Yes?
If no data is produced in the write-back stage, why do we even have a write-back stage? Why not just always write back from the
Well, because it takes time to write, right? So remember, we pipeline these operations because if you write from memory stage, then you extend how long that memory stage is. That's a good question, but now you increase your cycle time if you do that. Okay? So if you have a load operation and a dependence instruction right after that, you cannot forward the value to the dependent instruction because the dependent instruction needs the value at the beginning of the execute stage, whereas the value is not available at that point in time. So you need to stall the add, if you will. Okay, so this is just if you actually have the forwarding paths, this code, you don't need any additional stalls. I need to do the analysis, if you will, because there's forwarding. Except for the load word case. In this case, the compiler can insert a null, for example. Or you detect this case in the pipeline. Okay? All right. Let me see. Maybe I will go through the pipelining of the LC3D quickly. Do you guys want to do it? Or okay. Yes. Some of you want. So let's take a look at the pipelining of the LC3D. LC3D pipeline is very basic. Basically, it's conservative in its handling of data and control dependence. It stalls on flow dependence. It stalls on a branch. So it's a very basic pipeline, similar to the basic MIPS pipeline that you're going to implement. I'll go through this relatively quickly, just to illustrate some of the concepts. Remember, this was the data path we studied for the microcoded multi-cycle machine. Well, LC3D pipeline looks a little bit different. Remember, our goal was to actually utilize this data path a lot better. LC3D pipeline will look a little bit different because we've added the pipeline registers, and you know the reasons why we added these. But the data path elements will remain similar, except they will get distributed across different stages. So, for example, if we go to the fetch stage, this element will look very similar to you, right? Where is that? There you go. There's a PC mux here. So in the fetch stage, there's a latch that determines the next program counter, if you will. And the target addresses come from somewhere. And they come from a different stage. Right? Because the target address becomes available, the branch's target address becomes available later on in the pipeline. Right? It doesn't become available right away. Okay? So the next PC can also be PC plus 2. Okay, so this is the data path for the pipeline. What else is needed in the pipeline? Basically, you need additional logic. So, and now you know, for example, one of the inputs to this logic is the stall signal. If you're stalling the pipeline here, you'd better not load PC. The stall signal should be fed here, such that the PC does not change, such that the stage does not move. Also, if you're stalling the pipeline, again, if you look at here, there's a load DE signal. One input to this logic is again a stall signal coming from later stages. If any of the later stages stalls, this logic evaluates load DE to 0, such that these latches do not change. And load PC, the program counter is also not loaded. Does that make sense? Okay. So this is the decode stage. I've already given you bits and pieces of this, really. This is the dependency check logic, and that's one of the stall signals that goes backwards. Okay. And some of the other data path elements just remain the same, right? You still need to have the elements to access the register file. You still need to have the elements to correctly source which source register you're going to source from, as well as which destination register that you're going to write to. Right? So all of these are generated in the data path. So this is the dependency stall. There's another stall signal that's generated here, which is the branch stall. Now we'll get to this in more detail, but you know whether or not an instruction you fetch to the branch right here. And if the instruction you fetch to the branch, what the LC3D, what this microarchitecture does is it stalls the fetch stage. Because the target address of the branch is not determined yet. Does that make sense? Okay. So what LC3D implicitly does is, and you will see this in your handout, is it increments the program counter every cycle. So it has an implicit assumption that the next instruction is always the next sequential instruction in the sequential instruction stream. And that's assumed. So in a sense, it stalls only if the instruction turns out to be a branch. So implicitly, it's doing some prediction. Right? And the prediction is that next instruction is going to be the next sequential instruction. And that's always true unless the instruction that's being decoded is a branch. So if it's not a branch, then the instructions move in the pipeline. Now if it is a branch, then we stall the pipeline. So this branch stall signal also goes into this load PC. So there are a bunch of inputs here. Okay. Let's see. Anything else interesting here?
Predicting the branch itself.
Okay, we'll get to that. Be patient. You could predict the branch itself too, yes.
When you mean branch, you also mean jobs as well?
So in this case, yes. In this case, it's also jobs. That's right. So if you look at your handout, it explains exactly for which instructions. But yes, it's for jumps too. Because we don't have the address of the jump available yet as well. You could optimize this design. It's not the most optimized design. But this is the design that takes most of the data path elements that are available and preserves them as they are. Okay, if you look at the address generation stage and execute stage, basically this is, remember this is the MAR mux that we had before. Now it generates the address here to access memory. And this is the ALU shifter, and you have some other logic that goes to the previous stages. Okay, and you can look at it. You can read the rest. Let me see if I want to point out anything here. And again, in this stage, for example, we send the destination register ID to the next stage. Why? Because we would like to check in the, to the previous stage, to the decode stage. Why? Because the decoded state needs to check whether there's an instruction that's dependent on that destination register ID. So you need to provide the right signals going backwards into the pipeline. Okay. And this is the memory stage. Here, branches are evaluated in this stage. Let me see. Okay, there it is. There is target PC. So the target PC is actually sent here. This is where the branch targets are computed, and maybe other possible branch targets are computed. And these are sent back to the fetch stage right here. So if you look at the fetch stage, you'll see target PC and cat PC coming in. This is the branch target. And then PCMux signal should be determined based on this logic. Okay. So what does this logic say? Well, I guess you'll need to evaluate it yourself. But if you have a branch here, and if the condition evaluates to true, and if this instruction here is valid, then you have some logic that determines the next the signal that controls where the next PC would come from. Right? Normally, if this instruction is not a branch, then the next PC mux should actually determine the next PC as PC plus 2. Right? Make sense? If this instruction is an unconditional branch, then the next PC mux should take the target PC. If this instruction is a conditional branch and the condition matches the condition checked by the branch instruction, then this PC mux should evaluate to the target PC again. If the condition doesn't match, then this PC mux should evaluate to this PC plus 2, the next sequential instruction. Of course, this, if you look at this, all of this is gated by the valid bits in the pipeline. If this instruction is a bubble, if you will, is an OP, then PC mux should really evaluate to PC plus 2, right? Because it's not a branch instruction. It's just an OP. Okay? So that's what I mean by gating all of the logic that matters with the valid bits. Okay. So we could have other stalls here. And you can, for example, we could have a stall, memory stall. Again, that needs to be propagated backwards. Okay, and this is the last stage. Okay, I'll let you go through this in more detail. But if you look at the control of this pipeline, there are 3 types of control signals. You have data path control signals. These are signals that control the operation of the data path. Control store signals. These are signals stored in the control store and that are used in the pipeline data path. And there are also stall signals. You all know very well what the purpose of a stall signal is. You need to ensure the pipeline operates correctly in the presence of dependencies. And you can go through this on your own, but these are the data path control signals. This is what's stored in the control store. And control store, in this case, is a little bit different, right? And data path control signals are also divided into stages. You don't have all of the control signals in all stages. And control store is a little bit different. It generates control signals for different stages. So if you look at this, for example, it tells you which stages need that control signal. For example, address computation related control signals are needed only in the address generation stage. So they need to somehow get there. Branch stall signal, whether it's the branch or not, is actually needed until the branch is resolved. Right? So that needs to be propagated. So that's how you can design the control stall. Okay, we've covered. Basically, you need a stall signal for any time when an operation in a stage does not finish in a single cycle. You need to provide all those state stall signals. For example, if the iCache is a miss, you have a stall signal. If you have a dependency in the decode stage, you have a stall signal for that. If there's a branch in the decode stage or the address generation stage or the mem stage, again you have a stall signal because that branch is not resolved. If the memory stalls, the cache stalls, you have a stall signal. So you can have many of these stall signals depending on different conditions. Any questions? This is all simple now. You can do your lab without any problems. Maybe. You're saying it's it's good conceptually, but when you implement things, that's when you really understand how things work. That's why we're having you implement all of these things. Okay. So let me briefly start control dependence handling so that you're primed for the next lecture, and you also need to do this in your lab as well. So the key question is, what should the fetch PC be in the next cycle? And I've covered this slide. You really want the address of the next instruction that you're going to execute, right? Well, we've covered this. If the fetch instruction is a non-control flow instruction, you know that the next PC should be the next sequential instruction. If it's a control flow instruction, then how do you determine the next PC? Well, we don't even know whether the fetch instruction is a control flow instruction. If you look at the different branch types, and I'll call them branches, different ISAs call different things, like x86, for example, everything that a lot of these things are jumps. There are conditional branches, there are unconditional branches, calls, returns, and indirect branches. Right? At fetch time, you know the direction of some of these things. Conditional branches, you don't know the direction because you need to check a condition. Right? And that condition is not available at fetch time, at least most of the time. Unconditional branches, calls, returns, and indirect branches, they're always taken. And the number of possible next addresses are different for each branch also. For a conditional branch, you have 2 possible next fetch addresses. Right? It's either the next sequential instruction or the target. For unconditional branches and calls, you have only 1 possible next fetch address. So if you can somehow compute that fetch address right while you're accessing the instruction cache, maybe you're able to fetch the target address in the next cycle. Right? But you've got to be careful. You don't even know if the instruction that you're fetching is an unconditional branch or a call. So that's what makes the problem interesting and a little bit difficult. Right? You can potentially compute the address, right? Assuming based on, oh well, I guess you may not have the instruction bytes yet also, right? Does that make sense? So the problem is, we're in this fetch stage. We want to determine what the next PC is right away. But we don't even have the instruction here, right? The instruction becomes available right here. So if you're computing the target address, even for an unconditional instruction, let's say unconditional branch instruction, and the target address comes from the bits in the instruction register, you need to have the instruction register instruction available to be able to do that. But we don't even have that yet. Okay. Returns and indirect branches can have many, many targets, right? For example, in return, if you do a return instruction MIPS, you return to an address that you stored with the call instruction, with the jump and link register instruction. Right? And that could, you don't necessarily know what that is. And indirect branches actually are also indirect based on the register. So when is the fetch address resolved? For conditional branches, if it's register dependent, during execution time, right? For unconditional branches, you can actually get the target at the decode stage, if it's a program counter plus offset kind of unconditional branch. Same with calls, potentially, unless it's an indirect call, if you will, which does exist in some ISAs. But I'll consider that indirect branches. Returns and indirect branches are actually resolved at execution, because those are register dependent. So we need to handle all of these instructions to keep the pipeline moving, right? But I'm going to mainly discuss conditional ones because those are some of the most difficult ones. Although indirect ones are quite difficult also, especially if you have many different possibilities. Okay, let me give you at a high level some of the solutions that people have looked at, and we'll end the lecture there. We'll go into more detail later on. But it's critical to keep the pipeline full with the correct sequence of dynamic instructions. Because if you cannot keep the pipeline full, you're not going to get one cycles per instruction, or one instructions per cycle throughput. Actually, if you can do the thought experiment. If you actually stall every fifth instruction, your throughput goes down by quite a bit, right? Maybe we'll prepare a question for the next homework. Note that down. Okay. So one option is to stall the pipeline until we know the next fetch address. This is the option that I described in LC3D. And this is a terrible option. Hopefully you guys are already sold on this. Because if you stall the pipeline until you know the fetch address, basically you're underutilizing your pipeline. Another option is to guess the fetch next address. How do you do that? How do you do that? Actually, well, you could guess the next fetch address is always PC plus 4. It turns out this is a good guess if the instruction is a non-control flow instruction. But if the instruction is a control flow instruction, this is not a good guess. Because a lot of the instructions are in the loops, control flow instruction in the loops. So it turns out you're better off guessing that the branch will be taken instead of not taken. This is, there's nothing set in stone, of course. This is based on a lot of workload analysis. But most of the branches are actually in the loops. And the number that's usually quoted is 60% of the branches, dynamic branches, are actually taken. So you would like to really guess as always taken. But that may not be always good also, right? Maybe you actually want to predict more intelligently based on what the program is doing at that point in time. And that's the idea of, so this is the idea of branch prediction, basically, guessing the next fetch address. When you get a control flow instruction, what is the next fetch address? How do you do it? Well, you can have very sophisticated ways of doing it. You can look at the behavior of the program at some point in time, collect information, and say, oh, this branch has gone this way in the past. So the next time, for example, one option is to do the last time predictor. Which direction did the branch go last time? Which target address did the branch take last time? So I'm going to do the same thing. Yes?
So you don't even know what the branch will get to the code phase.
That's right.
So you're automatically going to probably load in PC plus or something right after that, or do you stall for that half one cycle?
So that's a good question, and we're going to fix that in the next lecture. But one option is to stall until you get the target, because you don't know the branch. The other option is to load the PC with PC plus 4, because most instructions are not branches, right? And it's better to load the PC with a PC plus 4 in that particular cycle. But we'll see an even better way of doing it. Somehow identifying while you're fetching that the instruction you're fetching is actually a branch. Can you guys guess how you could do that? Well, think about it. Okay. The other option is to employ delayed branching. Basically change the semantics of the branch. And we will start with this in the next lecture. Change the semantics of the branch such that the branch doesn't take effect until the condition of the branch is computed. Right? So if you have if it takes 3 cycles for your pipeline to compute the target address after a branch, change the semantics of your branch in the ISA, saying that this branch will not take effect until the next 3 instructions are executed. That's the idea of a delayed branch. And hopefully it makes more sense now, because this way you avoid the problem, right? This way, again, software handles the dependence, if you will. The software needs to ensure that the next 3 instructions that come after the branch are actually independent of the branch. And they're always executed. And we'll see this. You could do something else. Again, right? Another option. This avoids the problem, right? There is no need to figure out what is the next instruction from this particular thread to fetch. Because if you actually fetch from another thread every cycle, they're all independent, right? One thread doesn't branch into another thread. Well, that's called a software interrupt, potentially. But we're not going to handle that right now. You can eliminate control flow instructions. That's another fundamental solution to the problem, right? Can you do this? You can, right? Because what I told you before is control flow is actually can be converted to data flow. That's the idea of predicated execution. Basically, if you eliminate the control flow instruction, eliminate the branches. I will not go into detail because we're almost out of time here. But this is another solution that we will briefly cover. But think about it. And think about if you can eliminate all control flow instructions. Loops may be a little bit difficult to eliminate. But if you have an if and else condition, then you can turn that into a data dependence instead of a control dependence. Another possible solution is when you get to a branch, fetch from both possible paths. Let's say you have a 5-stage pipeline and the branch is resolved in the 4th stage. In the next cycle, you can fetch from one path, PC plus 4. In the next cycle, you can fetch from the target. And you can interleave these 2 different paths in your pipeline. And when the branch actually resolves, you pick one path and selectively invalidate instructions that are not on the correct path. Make sense? So I'm stretching your imagination a little bit. These are some of the techniques that people have developed. And we will go into more detail, of course, into how to guess the next fetch address, how to employ delayed branching, and briefly how to do something else as well in the next lecture. And if we have time, maybe we'll go through some of these other things that are actually employed in some real process. For example, Intel ARM ISA, a very common ISA, has predicate execution implemented. Every instruction has predicate bits. And that predicate bit is set based on a condition. And the instruction is conditionally executed. If that predicate bit is set, the instruction takes effect. If that predicate bit is not set, the instruction is an OR, essentially. And there's an instruction that sets that predicate bit. Okay? Okay, well, I'll see you in the next lecture. And if you haven't picked up your homework, this is the right time to do so.